So we're going to look at the technique, separation of variables. Now, it's possible to do it if we could rewrite the derivative in the form function x times some function of y. If we can do that, then we could rewrite it. It'd be possible to separate the y's and the x's and end up with something like this. The integral of dy over gy is equal to the integral of function x dx. But then once we've got that in that format, we can handle the problem. Okay. Now, thing with separation of variables, trivial solutions we've got to watch out for, because I'm dividing by the function of y in this case. So if the function of y could equal 0, then technically I'm dividing by 0. So what you should find happening is, if function y equals 0, that'll create a trivial solution. Because go back to the original one. If the function is equal to 0, then that means our derivative is equal to 0. Therefore, the function must have been a constant. And so the solution to that function equals whatever, if it's linear I suppose, would create the situation. So we need to check to see trivial solutions. Always perform just a quick mental check. You don't have to write it down, but mental check to look for trivial solutions, see if they work. So we'll have a look at this one. The derivative is x squared times 1 plus y squared. So I can separate the variables out here. I get the integral of dy on 1 plus y squared is the integral of x squared dx. So left hand side we've got inverse tan. Right hand side x cubed on 3. It really doesn't matter which side you put the constant on. So I've put it on the right hand side with the x because I'm going to make y the subject. So it makes sense to do that, I think. So y would end up being the tan of x cubed on 3 plus a constant. In this case, I don't have the trivial solution problem, because 1 plus y squared, well, that's never going to equal 0. So I don't have that problem. Okay, let's have a look at this one though. The derivative is x squared y. Now in this case, y equals 0 is a trivial solution, because if that was a solution, it would satisfy that the derivative is equal to 0 and the function itself is y equals 0. So yes, we have got a trivial solution for that one. Let's look for the non-trivial ones though. So separate the variables to y and y. That'll integrate to give log y. And the right hand side, once again, x cubed on 3 plus a constant. Exponentialise both sides. But notice the constant now goes into the power. So y is e to the power of x cubed on 3 plus c. But then using our log laws, e to the power of c, well, that's going to be a constant anyway. I mean, it's a positive constant, so everything's fine. Does it really matter? Well, we are saying absolute value of y is equal to that, so I suppose it is important for that to be a positive number. But it's all good. C e to the power of x cubed on 3. So I've just then said, well, y equals another constant a, which might be plus or minus, because remember we're saying the absolute value of y is this, so y could be plus or minus. So I've just given it a different letter. It's still just a constant. But don't forget the trivial solution. So therefore y is equal to 0 is a possibility, but the other possibility is a e to the power of x cubed on 3, and an initial value problem. So I'm going to do it as a definite integral. I'll always use definite integrals when I'm solving an initial value problem. I just find it easier. So we're going to separate the variables, but notice with this one, instead of saying dy over cos squared y, I've turned it into sec squared straight away, only because we know the integral of sec squared. So that's why I did that. And then on the other side, we have dx on x squared. Now they have told me that when x is 1, y is pi on 4. And we're trying to link together y and x. Integrate sec squared. We get tan. And we're going from pi on 4 to y. And on the right hand side, we get minus 1 on x. And we're going from 1 to x. That's right. So subbing in, tan y minus 1 is minus 1 on x plus 1. Rearranging all that, I've made y the subject. But there we go, we've got y equals the inverse tan of 2 minus 1 on x. So yes, dy dx equals x squared plus y squared on 2x squared. And when you first look at that, it appears that you can't separate it. Remember, because we're looking at for a function of x times a function of y. Well, you have a little trick here. Why don't I do a substitution? And instead of looking at that and thinking it's a function of x and y, I'm going to say it's a function of y divided by x. Okay? So if I let u equal y over x, in other words, y is equal to u times x, I can rewrite that as a half plus a half y on x squared, which will become a half plus u squared. Yep. All right, but what will dy dx become? Because remember, y is now equal to u times x. So I've got to use a product rule. Write down the first, u. Diff the second, well, x, well, that's 1. Plus, write down the second, x. Diff the first, du dx. So my equation now becomes u plus x du dx equals a half plus a half u squared. I now have a situation where I can separate the variables. Okay, I'll move that u to the right-hand side. Everything on the right-hand side in terms of u. My x is all on the left-hand side. I'll write it all as one fraction to make life easier for myself. Ends up being 1 minus u squared over 2. But separate them out. So I've got 2 times the integral of du on 1 minus u squared is the integral of dx on x. So 1 minus u is the log of x plus a constant. Okay, so 1 minus u is equal to 2 over the log of x plus a constant. So I've made u the subject, but remember u is y on x. Now I'll put that back into it, multiply by x, and I have this wonderful expression. 13C's on our separation of variables. We'll give that a go.